Okay, welcome. We're going to be covering our section 2.2 in the textbook. We'll be talking about transforming data by adding, subtracting, multiplying, and dividing each data point by a constant and looking at the effects of that. So let's first look at adding and subtracting. Here are the original 12 salaries we looked at about 2 or 3 classes ago. And again, the median was right here in the middle. And our median, if you remember, was 34.5. The range was 156,000. Now, if I wanted to add $6,000 to every salary, okay, here's the new data after we add 6,000 to everyone's salary. And now if we look at our median of the new data, so halfway between, so that'd be 40.5 thousand, our range is still the largest minus the smallest, which gives us 156,000, the exact same as what we started with. So we notice that the median has shifted up by 6, whereas the range or the measure of the spread stayed the same. This is something we just want to keep an eye on. Now let's look at how it affects the spread of the data. So here's my original data with a mu of 10, so that's my center point measure, and I'm told that the standard deviation, because remember that funny symbol of standard deviation, is 2. So that means it's 2 this direction and 2 this direction. Well, I'm going to add 6 to each data point. And when I add 6 to every data point, the center of my data has now shifted to mu equals 16. My standard deviation, though, is still the same. And let's go ahead and put that. Standard deviation equals 2 still. If I were to subtract, you'd probably guess that there's going to be no change, and you'd be right. So here's my original data. Here's the shape of it, the distribution. If I subtract 6 from every data point, I get a new center, which is that mu equals 4. But my standard deviation stays the exact same. So the shape is the exact same. It's just shifted left or right. It shifted to the right when we added, and it shifted to the left when we subtracted a constant. So anytime we add or subtract a constant, our center adds or subtracts by that constant amount. The spread remains the same and the shape remains the same. Okay, let's come over and take a look at multiplying now and dividing. Okay, if you turn over your paper, we're looking at multiplying and dividing your distribution by a constant. So we're going to take every single data point in this data set and multiply everything by 3. Well, I only have 2 data points, so I'm multiplying each one by 3, so these are my 2 new data points. Originally, my median was 1.5 with a range of 1. But I've multiplied everything by 3 now. And when we've multiplied everything by 3, the new median now is 4.5. It's halfway between 3 and 6, and our range is 3. So when we multiply, our big numbers are increasing more than the small numbers. Because the numbers are changing at different rates, the spread between them is growing larger. So let's come back to our salaries. Again, our original median was 34.5 thousand with a range of 156,000. I'm going to multiply everyone's salary by 1.06, which is in essence giving everyone a 6% salary increase. Here's the new data values. My median is right here between the 6th and 7th data point. Okay, so here's our median halfway between these two. So our transformed data set, we have a median of 36.6 with a range of 165,000.4. And notice that our data now, the range has gotten larger when we've multiplied. So the range is spreading out. And if we were to look at the shape of these, so here's my original data, this kind of sharp peak. It has a mean of 4 and a standard deviation of 2. Again, same one we started with on the front page. And I'm going to multiply every data point within this distribution by 2. When I do that, my mean increases from 4 times 2, so it gives me a mean of 8. And my standard deviation has also increased by 4, so it's spread out. We still have the same number of data points, so it's no longer as high. The frequency has gone down for each value. So it's spread our data out quite a bit. In Algebra 2, we might have called that a horizontal stretch, that we're stretching the data out. And let's look what happens when we divide. So again, my original data is right here with the mean of 4 and standard deviation of 2. And I'm going to divide everything by 2. So my new mean is at 2. My new standard deviation is only 1. So in effect, what we've done is taken and squished that data together. When we divide, it's given you a much tighter spread. So things are closer together. So we would say the center is multiplied or divided by the constant amount. In terms of the spread, it also multiplies or divides by the constant amount. And the shape, it generally is the same shape, that there's just a single peak. The spread of it changes slightly, but it's the same general shape. Okay, let's take a look now and talk about real life. So we're going to talk about money and income, our wealth and inequality. So let's take a look at what a stock is. It's a small ownership or share in a company. So if you were to buy a stock in something like Google or Nike or Adidas or Coca-Cola, if you are a part owner, granted a very tiny owner, that there are hundreds of thousands of people who are owners also. And the more stock you own, the more say you have in how the company is run. But if the company makes profits and gains value, your stock value rises. If the company suffers losses, your stock loses value. And we have stocks that you could buy individual ones, such as Coke or Google or any of those, or you could have an index. And an index tracks what the whole market is doing as a whole. So in general, it's a little less risky because it's buffered by the different types of stocks. But the S&P 500 is an index that tracks the value of stock from 500 large American companies. And it's a fairly good indicator. It's well respected. And now what we're going to do is take a look at stocks and see what happens with our wealth over time. And in general, the stock market tends to go up over time, so it multiplies. So let's say we invest $185 in the S&P's 500 index stock fund in 1950. So that's 70 years ago. And let's see what happens. So each year, we multiply by 1.04, which is the gain in value per year. And that was inflation adjusted. It means we subtracted inflation from our gains. Then we again increase by 4%, increase by 4%, et cetera, et cetera, et cetera, until we reach the year 2020, when we now have $2,880.75. So if we were to look at what this looks like on a graph, here's my years, all the way up to 2019, my value. So I started at $185, and this sort of jagged line here is what's actually happening with the stock market with the S&P 500. The curved line is if we gained exactly 4% every year. So you can see it's a exponential growth, nice and smooth there, but it pretty much matches what the S&P 500 did. And now the crux of our question and the reason we study stats is to be able to look at things in the real world. So let's take a look here at the US family's real wealth over time. And we're defining wealth as all your assets, your stocks, your home value, bonds, anything that contributes towards your money or your net positive, basically. And if we look for the bottom 90% of the families in the United States, wealth has grown. So that's good, right? If we look from 1950, so here's where they started. And after the year 2012, here's where they are. So there's definitely been an upward trend. Obviously, there is some down points right here, the year 2008, when we had the downturn, the Great Recession. But this was for the bottom 90% of the families in the US. So let's take a look now. What about the top 10% of the families in the US? And if we take a look here, notice our scale. Here we were going from 20,000 to 140,000. When we add in the top 10%, we now have to go all the way up to $3.5 million to compare these. So this pink line is still my bottom 90%. So it's the same graph right here, but because the scale got squished down, all of that got squished down also. So it's very difficult to see. There's a tiny little down part right here, which matches this in 2008. This blue line, though, is your top 10% of the US family's wealth. And notice where they started out, they were kind of close together, but look at after 60 plus years how far apart they are now. And each one of these was just gaining the exact same amount. They're gaining 4%. And let's see what happens even further. Let's add in the top 1% of US families. So now we've got to go up to $16 million on my scale, so much greater. So again, everything's getting pushed downwards. So in pink is the bottom 90% of US families, the growth of their wealth, which looks, at this point, it looks almost flat with this scale. My top 10%, and this dark blue line represents the top 1% of families in the United States. Look at how far apart these are now. This family is ending up at 14 million, whereas our bottom 90% ended up at about 84,000. And we thought that the 84,000 was good growth. But when you compare it to what else is going on in the country and the other families, look at the difference here. So the first question for you to think about is, why is wealth inequality increasing? What does that have to do with scaling? Think about, are we adding or are we multiplying here? And then, is wealth inequality a problem? If so, what do you think we should do about it? And if not, why is it not a problem? Now, I'm not going to give you my answers right here. I just want you to think about that. And finally, let's see what happened to the spread of our incomes. So we're going to look at the very low start of $185 in 1950 compared to a high starting value of $100,000. So again, two different families and where they start. How far apart are these two data points? Well, 100,000 minus 185 gives us $99,815. So in the beginning, that is the difference between them. And let's let each family's wealth grow by 4% each year. So each year we had 4% till we get to 2020. Our bottom 90% end up at $2,880, but my top family ends up at 1.557 million. Look at the difference between these when we finish up. Greater than $1.5 million difference. So keep in mind, multiplication increases the spread. So repeated multiplication really increases the difference or the spread between these two values. Okay, so now we're going to go ahead and take a look at your chapter and work on the problems. Let me know if you have any questions.